Welcome to Selection with Sathi. Today we cover segment trees, a powerful data structure for range queries and updates in O of log n time. We will build a segment tree step by step, trace range queries, point updates, and master lazy propagation. This topic appears regularly in GATE CSE and competitive programming. Let us begin. Let us start with the structure of a segment tree. A segment tree is a complete binary tree stored as an array. For a node at index I, its left child is at 2i plus 1 and right child is at 2i plus 2. The leaf nodes store the original array elements. Each internal node stores the result of merging its two children. For a range sum tree, the internal node holds the sum of its children. We allocate an array of size 4n to be safe. The height is ceiling of log 2 of n, giving O of log n levels. Now let us look at the build function. Look at line 1, the function takes the array, tree, node index, and range start to end. Line 2, if start equals end, we are at a leaf. Store the array value at line 3. Line 5, compute the midpoint. Lines 6 and 7, recursively build the left and right children. Line 8, merge the two children. For range sum, we simply add them. Build visits each element exactly once, so the total time is O of n. This is a one-time cost. After building, queries and updates array O of log n. Point update changes one element and fixes the tree. Look at line 2, if start equals end, we reached the target leaf. Set the new value at line 3. Line 6, if the target index is in the left half, recurs left at line 7. Line 9, otherwise, recurs right. Line 10, after the recursive call returns, recalculate the current node by merging its two children. Only the nodes on the route to leaf path are affected. That is O of log n nodes. So point update is O of log n. Range query is the heart of segment trees. There are three cases. Look at line 2. If the query range is completely outside the node range, return 0. This is no overlap. Line 4. If the node range is completely inside the query range, return the stored value. This is total overlap. Lines 6 through 9, for partial overlap, recurs on both children and merge the results. The key insight is that at most O of log n nodes are visited per query. At each level, at most two partial nodes are explored. This gives us O of log n time for any range query. Lazy propagation solves a critical problem. Without it, updating a range of elements requires O of n log n time. With lazy, range updates become O of log n. The idea, instead of updating all leaf nodes, we store pending updates in a lazy array. Look at lines 2 through 7. Before any operation, push pending lazy values to children. Lines 10 through 14. If the node range is fully inside the update range, update the node value and mark children as lazy. The update is deferred until those children are actually needed. This is essential for competitive programming and frequently asked in GATE.
Let us build a sum segment tree from array 1, 3, 5, 7, 9, 11. First, the 6 leaf nodes store 1, 3, 5, 7, 9, 11. Moving up, The first pair, 1 plus 3 equals 4. Next pair, 5 plus 7 equals 12. The node covering index 4 and 5, 9 plus 11 equals 20. Going up one more level, 4 plus 5 equals 9 for range 0 to 2. And 12 plus 20 equals 32 for range 3 to 5. Finally, the root, 9 plus 32 equals 36 at the top. Verify, 1 plus 3 plus 5 plus 7 plus 9 plus 11 equals 36. Correct. Now query the sum from index 1 to 4. Expected answer, 3 plus 5 plus 7 plus 9 equals 24. Start at root, range 0 to 5. Partial overlap with query 1 to 4. Recurs both children. Left child covers 0 to 2. Partial overlap. Recurs its children. Node 0 to 0, no overlap since 0 is less than query left 1. Return 0. Node 1 to 2, total overlap, both indices inside query range. Return 8, which is 3 plus 5. Right child covers 3 to 5. Partial overlap. Recurs. Node 3 to 4, total overlap. Return 16, which is 7 plus 9. Node 5 to 5, no overlap since 5 is greater than query right 4. Return 0. Merge, 0 plus 8 plus 16 plus 0 equals 24. Correct. Let us update index 2 from 5 to 6. Start at root, range 0 to 5. Index 2 is less than or equal to mid 2, so go left. Node covers 0 to 2. Index 2 is greater than mid 1, so go right. Node covers 2 to 2. This is the leaf. Update value from 5 to 6. Now propagate back up. Parent node 0 to 2, recalculate 4 plus 6 equals 10. Was 9. Root node 0 to 5, recalculate 10 plus 27 equals 37. Was 36. Only 3 nodes changed on the root to leaf path. Time, O of log n. Now lazy propagation in action. Add 3 to every element from index 1 to 4. At the root, range 0 to 5, partial overlap. Recurs both children. Left child 0 to 2, partial overlap. Recurs its children. Node 0 to 0, no overlap, skip. Node 1 to 2, total overlap. Add 3 times 2 equals 6 to this node's value. Mark its children as lazy with value 3. We do not go deeper. Right child 3 to 5, partial overlap. Recurs. Node 3 to 4, total overlap. Add 3 times 2 equals 6. Mark children lazy. Node 5 to 5, no overlap, skip. Total, only 7 nodes visited instead of updating 4 leaves individually. The lazy values will be pushed down only when those children are queried later.
Quick exam tips. First, always allocate 4 n space for the segment tree array. Second, iterative segment trees are faster in practice, but recursive ones are easier to code and extend. Third, use lazy propagation whenever the problem involves range updates. Without lazy, range update is O of n per update, which defeats the purpose. Fourth, gate frequently tests range sum and range minimum queries. Know the 3-case logic by heart. No overlap returns identity, total overlap returns node value, partial overlap recurses both children. For more DSA concept videos with code walkthroughs, download the Selection with Sathi app. Like and subscribe. Thank you.